in the next couple weeks, we're going to go from where we've been, which I think is a fairly narrow set of concepts. Like we've stuck around the same kind of ideas, maybe 2 or 3 key ideas, but related ideas. We've talked about electric forces. We've talked about circuits. We've talked about magnetic forces. There's quite a bit of connections between those guys. Charge and current have been, playing a role basically every day, every discussion, every lab, every homework assignment or question, up until this point for basically half a semester. And in a little bit of time, we're going to go from where we're at, and we're going to be talking about magnetic induction today, electromagnetic induction, like the lab, before break, not last week's lab. Chapter 33. But if you kind of look at the next couple chapters, chapter 33 is called electromagnetic induction. Chapter 34, I can't remember if it's the entire title, but part of the title is electromagnetic waves. And then we're gonna kind of jump a little bit out of chapter sequence and kind of jump back to some chapters around, let's see, let me get the numbers here. Just show this up here. We've been going kind of straight through electricity and magnetism, pretty much just right down the line. And we've gotten to magnetic field. And now we're going to be talking about electromagnetic induction. We have some, we will continue to electromagnetic fields and waves. That's the other half of the title of chapter 34. And then before doing AC circuits, which we are going to do, we're going to jump out of chapter sequence here and end up doing some chapters in here about optics, waves and optics, part 5, like chapters, I think there's questions from 22, 23, 24, maybe especially 22 and 23. So these are in the waves and optics part of the textbook, and the titles are things like ray optics and wave optics. Maybe there's a bit of a connection there to electromagnetic fields and waves. So we're going to have kind of taken some pretty big steps kind of conceptually and start to kind of pull together electricity and magnetism to some other branches of science and physics and engineering. In particular, where the big connection there is we're going to start eventually, not today in class, but soon, we'll be talking about light. And there's a pretty big connection between electricity and magnetism and light. So that is one of the things we're going to go for. Electromagnetic waves is part of the title of chapter 34. What's an electromagnetic wave? What's an example of an electromagnetic wave? Red light, blue light, infrared light, ultraviolet waves, X-rays. These are all examples of electromagnetic waves. So there's some steps there. And in order to get from where we are to there, we have to start kind of seeing some connections between electricity and magnetism and the way that they work together very closely. And the focus that we're going to have in that is we're going to really focus on the electric field and the magnetic field, the electric field and the magnetic field. And we'll see some interesting connections made. One reason I bring this up is, so we have 4 labs between now and the end of the semester, actually just 4. And 2 of the 4 are optics labs, where the equipment is like a light source, turn the lights off in the room. We'll be doing this tomorrow. And kind of like with circuits, we got to circuits much earlier in the lab Thursdays than we did in the class. We're going to be doing some optics. It's pretty fun. It's not the most difficult experience, so it kind of can work well even without a whole lot of context prior to that day in lab. So we're going to be doing that tomorrow, and I think a week from tomorrow will be 2 labs involving light and put some obstacle in the path of the light. What happens when the light hits this kind of curved surface? What happens when the light hits that kind of curved surface? And we'll be getting there through the connecting step of electromagnetic fields. And then we'll start to do other things after that, kind of out into maybe later November or into December. Go back to circuits, basically, which are the other 2 labs we have yet to do. So We're going to do some quantitative work with electromagnetic induction today, some detailed kind of calculations, whereas up until now, at least in the class on, let's say last Wednesday and Friday, come on. Yeah. Couldn't get the thing to stay up screen. We've done some qualitative stuff of figuring out, is there going to be an effect? And if so, will it be maybe clockwise current or counterclockwise current? And the key idea there in understanding the directions is identify that there is a flux and then identify what is happening, what's the direction of the flux, and is it increasing or decreasing? Because the key equation is Faraday's law, which I'll kind of put up here, but this is the situation we're going to kind of talk through, but I'll just kind of hop Faraday's law on here. So kind of the two main equations from chapter 33 would be the definition of flux, which is B dot dA, and I'll just say that this will equal B dot A if the magnetic field is uniform. We don't have to do an integral, we can just multiply. If the magnetic field is uniform, and this is the magnetic flux through a surface, like a 2D surface. Maybe I'll say a 2D surface. And basically the 2D surfaces we're interested in, what are the 2D surfaces we're interested in? Usually an aluminum ring, a bunch of wrappings of wire, something like that, where there's a possibility of current flowing around the edge of that 2D surface because it's a nice conducting material. Typically like a coil of wire. So that's kind of a definition. And then in terms of that, we are often taking the derivative of flux with respect to time. If there's a number of wrappings, we can multiply by that. I think I'll write the n here. And then if we do this, this is Faraday's law. And how do I read this? This is about a loop. This is intended to be applied to a loop. So you calculate the flux through the loop. If it's increasing or decreasing with time, there's going to be a non-zero time derivative. If there's a number of wrappings, you multiply by that. Minus sign is something we've talked a bit about. And what have you calculated? What have you learned by doing negative n d phi dt? You've learned the voltage induced around the loop. So this is the EMF, or voltage induced around the loop. We can't kind of associate this voltage with any particular point in the loop. We can't say, oh, it's like there's a battery on the left wire of the loop or the top wire, but somehow all the way around the loop, there ends up being a voltage. EMF, or voltage induced around the loop. And most commonly, we would either be finding a voltage or maybe we'd be finding a current, but you would use Faraday's law to find the voltage. And then if you needed to convert voltage to current, you would just do some basic circuit work and think about Ohm's law and look at the rest of the details of the circuit. Maybe there's some resistance. So how do you get a changing flux? You could either change the magnetic field, stronger and weaker. You could change the area of the loop, or you could change the angle formed between the, you could change the orientation of things because the dot product will depend on the orientation of the vectors. You know, maybe like, what's the dot product? Magnitude of the first vector, magnitude of the second vector, cosine of the angle between them. And we've spent some time thinking about what does the area vector mean? This is a fairly common notation that could show up in a lot of different fields. Is we need to associate a vector with a 2D surface. And the way we would do that is that vector will typically point perpendicular to the 2D surface. That would be a way to easily convey the orientation of the 2D surface by just having to communicate one vector. Instead of saying like the blackboard is in the X and the Y direction, you just say, oh, the blackboard's perpendicular to the Z direction. Okay, so let's do this quantitative. Oh, and the minus sign. I do want to say something about the minus sign. What's the minus sign? Lenz's law explains, or kind of explains the meaning or the interpretation of the minus sign. So a lot of times what we would do is, similar to finding the force between a bunch of charges, between two charges, I should say, similar to finding the force between two charges, I would maybe just take the absolute value of some force equation to find the strength of the force between the two charges. And now I know the strength of the force, but it's a vector. So how do I figure out the direction of the force? I take the absolute value of this to get the strength of the EMF, and then I want to now think through the direction. And I just go to some other kind of rule that helps me work out, okay, now I figure out the direction of the magnitude that I just found. In the case of charged particles, what's the rule you go to figure out the direction of the force? You know, like charges repel and unlike charges attract. And of course, you could do that all together and get the vector magnitude and direction all in one calculation, but a lot of times we kind of just make it a two-step process, take absolute values and get magnitudes, and then do the rule about directions to figure out directions. So Lenz's law explains the meaning of the minus sign, and we would often use words like the induced effects on the left-hand side are always in a direction to oppose the change that created them. So Faraday's law, Lenz's law, and we talk about magnetic flux. Okay, so here's the situation that I think we're going to talk about for a good chunk of today and try to just pull out different features of this. So this is supposed to look like we have a region of magnetic field, but it's only kind of of limited size. So it's probably a little bit unrealistic, but just kind of imagine that the magnetic field is basically zero everywhere outside this box and just jumps to be, what does it say there? 2.5 Tesla everywhere inside the box. Basically, you could almost kind of think of it like somebody's holding a really large like it's kind of like you're passing between the poles of that big horseshoe magnet. And to get the orientation right, if these are dots pointing out of the page, then somebody's holding the big flat north pole of the horseshoe magnet kind of above the plane of the page, and they're holding the big flat south pole on the other side, and this object of interest is going to pass in between. Now, realistically, it's going to go from a region of zero magnetic field when it's far from the magnet to a strong magnetic field when it's in between. We'll make that a little bit artificial and just say like the magnetic field is just strong and present inside the box and nothing, zero, absolutely absent outside the box. So now what are we going to do? We're going to have a coil. There's going to be some resistance here because there's a bunch of wrappings. There's a bunch of wire there. So there's some resistance, but not a whole lot. It's 50 turns. Each turn is, however many centimeters that is, 60 centimeters for the perimeter. So we have a pretty long chunk of wire here. It's just been wrapped up. So there's 4 ohms of resistance, a small but non-zero amount, and there's a bunch of wire in these dimensions. And this is going to be moving to the right. So, you can think of some of those different demonstrations at the different stations 2 weeks ago. We're moving a coil into and through a magnetic field. So it's going to move at, that's 10 centimeters per second, 0.10 meters per second. And then just for the timing issues, let's just say time 0 is when the leading edge gets to the edge of the field. So maybe I'll just kind of write that in here. So, I think I'll kind of, it's going to move straight across, but I think I might just kind of show it moving down a little bit. So it doesn't actually move down, but just to kind of separate the pictures here. So this is going to be time 0. Because we might make some graphs, we might write down some equations. Okay, so the graphs I'd like to make, the information EMF around the loop. EMF, but that's measured in volts. It is voltage. And this is time measured in seconds. I'd like to make these two graphs here for this scenario. So we'll just, do them one at a time. So let's think about this here. And I think we can kind of build this up step by step. So let's just kind of figure out the times for a couple key moments. This is a key moment. Then like this will be kind of a key moment here, like the moment at which the coil is kind of fully in the field for the first time. And then this will be a key moment when it's about to start, when it gets to here, that's a key moment in time. And like this is a key moment in time. And then it just keeps on going and it's over here. And the whole time it's just going to move to the right, move to the right, move to the right at the same V, which is at 10 centimeters per second. Okay, so let's just first of all, just kind of do the easy distance, time, speed stuff. What are these 4 key moments in time? Well, it's 20 centimeters long and it's going 10 centimeters per second. So it takes 2 seconds to enter the field. So, one key moment is 0 seconds. Another key moment would be 2 seconds. This is T equals 2 seconds. What is this? Well, the leading edge has gone 60 centimeters to get from the first picture to the third picture. So this one is 6 seconds and this one is 8 seconds. So I'm just going to kind of mark out those key points here. Kind of 1, 2, 3, 4, 5, 6, 7, 8. I maybe should give myself a little more space, but the key ones are 2 and 6 and 8. 1, 2, 4, 6, 8. Keep going. Okay. So let's do the easy parts first. What is the flux through the coil? Until it gets to the field, there's no flux through the coil. So everywhere out here, there's no flux, right? Before you reach there. And then the other easy one, let's just jump everywhere beyond, every moment beyond 8 seconds, there's no magnetic field piercing the loop. And so there's no magnetic flux from 8 seconds onward either. Zoom out a little bit less. Okay. So those are a couple key ones. Okay. And then somebody tell me what you might kind of do next or consider next. We'd like to make this graph of flux versus time and fill in the 0 to 8 second, interval.
Well, if it's exactly a per area thing, then we'd only count the area in the field, right?
Yeah, I should probably draw a picture where it's partway in. I'm going to run out of space here, but I'll draw a picture where it's kind of like partway in. And so we can have that one to refer to. I don't mean it to be halfway. I just want it to look like it's partway in. All that really is receiving flux is the chunk that's in the field when it's partway in, partway out. That's kind of like the integral idea. If I integrate B dA, all of this area is feeling 0B, and so the integral is 0. So all that contributes flux is the magnetic field, the area that's inside the field. Yeah, go ahead.
The area is also always perpendicular to the field, so we don't have to do any cosine.
So there is the angular stuff to think through. One thing to notice is whatever the angular stuff isn't going to change as we move across there. And what is the angle that is formed between the area vector for the green loop and the magnetic field the entire time? The area vector would point out of the page perpendicular to the green loop. So that'd be like a 0 degree difference in angle between B and A, and cosine of 0 is 1. This is the arrangement this is the orientation of the loop to get the most flux we can get. So we can kind of set that part aside. So we got our flux is BA cosine theta. Well, the cosine theta is a 1, and all that matters is the area inside the field. So what's going to be true about the flux from 2 seconds to 8 seconds? what's going to be true about the flux from, you know, this moment to this moment? It's going to be some large but steady amount. We'd like to find that number, but whatever it is at 2 seconds, you know, it's going to be the same from 2 to 6 seconds, and it's going to be some value. I'd like to find that value. What is the max flux going to be? Well, that'll be the full area of the loop times the magnetic field. And what is the area of the loop? 0.2 meters times 0.1 meter times 2.5 Tesla. So, you know, wherever that comes out to be 0.02 times 2.5, 0.05, I think. 0.05. So the max flux is going to be, by max, is going to be 0.05 Weber. And that's just full area of the loop times magnetic field, which is 2.5. So now we can work this out. We can think about this. But basically, what's going to happen over the 0 to 2 second interval of time? It's going to linearly increase. Every little delta t that goes by, we've added another uniform little sliver of area to the inside of the loop, inside of the field panel. So this is going to be nice and linear. And this is going to be nice and linear the other way, like that. We could write this out. Let's just say phi max is BLW, magnetic field times area, length times width. And let's just kind of do a little bit of that and a little bit of that. And by the way, we've made a bit of a choice in sign. What direction is the flux through the loop? It's in the magnetic field direction, which is out of the page. So I guess when I'm graphing this, positive flux is kind of like out of the page flux. And negative flux would be, we don't have any negative flux, but it would be representing magnetic field piercing through the green loop this way instead of magnetic field piercing through the green loop that way. All right. We could write equations for these lines here. What's the equation for that line there? Well, it's BLW over this interval of time, but this interval of time was the length over V. You know what I mean? Length is 0.2 meters over V, 0.1 meter per second squared. So you could write that out. So what is this graph going to be here? We'll write that in a second. What is this graph going to look like here? And now we do Faraday's law. We take a derivative of the first graph, and then maybe we pop a minus sign on it, and we multiply by a bunch of wrappings if there's a bunch of wrappings. But basically, we take a derivative or a negative derivative. So what is this going to look like? When will we be inducing EMF around the loop? We won't be inducing any EMF around the loop when it's outside of the loop. Maybe not too surprising. 1, 2, 3, 4, 5, 6. Won't be inducing any EMF then, but we also won't be inducing any EMF while it's fully inside the field. And nothing really happens to the loop of much interest. Nothing super exciting happens when it's in there fully, but while it's entering the field, something happens. While it's exiting the field, something happens. So what will this graph look like? I now need to take the derivative of this, so I need to know the slope of these lines. So what are the slope of those lines? We could put numbers to this. Of course, it's 0.05 over 2 seconds, right? That's just numerically the slope. And that'll be the value over here, except we're supposed to multiply by 100 wrappings, or sorry, 50 wrappings, 50 wrappings. So numerically, the values are going to be, the max is 0.05 divided by the interval of time, 2 seconds. The slope here is 0.025, and of course, negative of the same slope. So positive 0.025, but I multiply that by negative 50. So the value over here is negative 1.25 while you're entering, and equal and opposite values, positive 1.25 while you're exiting. So it's basically kind of like a little plateau down here and then a little plateau up here. And if you kind of, maybe you could put open circles or something, but don't care too much about some of those issues. What is this value? Negative 1.25 volts. And this is positive 1.25 volts. So it looks about like that. if you were looking at a little needle, like the little needle that could flick either direction near the front of the room when doing that or apparatus, the needle won't be doing anything while you're in the field, while you're approaching or out of the field, but while you're entering, you'll see it flick one way and sit there for a couple seconds, and then it dies out, and then it flicks the other way. And maybe depending on the arrangements, you'd see first a negative current or a negative voltage, and then later on you'll see the opposite, maybe a positive voltage or current. Let's just kind of say what these would be here. What is that equation right there? Or what is that slope? The slope is proportional to the magnetic field. It's proportional to this dimension of the loop W, and it's V. You can just kind of think of what that is. You can kind of see it here. It's this divided by this. BLW divided by rise BLW minus 0 over run, which is L over V minus 0. That's where we got the 2 seconds from. So the slope is BWV there, and here the slope is negative BWV. And with our numbers, I think that should come out to be the number that can be multiplied by 50 or so. So this right here is negative N BWV. It's basically this slope multiplied by negative N. And then here, I guess we get the same thing, positive N BWV. The length of the loop doesn't affect this graph at all. I mean, that's not quite true. It doesn't affect the y coordinates. What is the length affect? It just tells you how long it takes you to enter. It takes 2 seconds to enter because it's that long. It takes 2 seconds to exit. But the values are dictated by the dimension perpendicular, the vertical dimension of the loop, and how fast you're moving the loop. How strong the magnet is, how many wrappings you have, and how fast you're moving the loop would be the main issues. If we took this and we divided by 4 ohms, we'd have a current. So we could now turn this into a current. What if the question had asked for the induced voltage? It's positive or negative 1.25 volts. Basically, it's 1.25 volts. What if it asked for the induced current? Well, we'll just divide by resistance. So the induced current, I would be negative 0.3125 amps. That's the same as that. And then this would be I is positive 0.3125 amps. So, 312 milliamps, something like that. Okay, what does the negative and the positive mean? That's something we should talk about. I mean, I'm just taking a derivative and putting a minus sign on it. This derivative is positive, I multiply by a negative. I'm just kind of mechanically getting these signs. But what does it mean to say a positive current or a negative current? Probably one of the orientations of current around the loop is associated with positive, ones with negative, but which one's which? And that's where you could use Lenz's law to figure out the direction of the current separate of all this, or you could, which one would you guess is considered the positive current orientation? And probably what's built into all this is out of the board is considered positive direction, and counterclockwise is kind of built in to be a positive orientation. So I would imagine that this is saying while you're entering, expect there to be some counterclockwise, while you're entering negative voltage or current. So I would expect that if we did Lenz's law, we'd come to the conclusion that while entering, we should have clockwise current flow. While in the field, we have 0 current flow, and fully in the field. And while exiting, we have counterclockwise current flow. So let's just kind of think that through from the point of view of Lenz's law. What if you didn't have to get the amounts? You just had to say, when is there current? And if so, what direction? I would say to myself, the flux is always outward in direction. It's always outward. What's happening to the flux while you enter the field? Is it increasing, decreasing, or the same? I have an increasing outward flux. How will the loop respond to an increasing outward flux according to Lenz's law? It likes the old number. It likes it 0, or when it builds up to 0.2, it's like, stay at 0.2, please don't go higher. So it tries to do something to keep the number down at the previous value, which means it's going to create into the page flux of its own. And so the current will run around the loop in whichever way, according to right-hand rule, will create its own magnetic field spiking through itself that way. So that would be, did I do that right or wrong? Out of the page and getting bigger. So it wants to do into the page is clockwise. Okay, I have to do that, or it's what's called negative. And then probably the reverse here. It's the reverse there. So that's all kind of built in there, is kind of the directional stuff. If you want to trust Faraday's law to get the direction and the number, that's kind of built into the system of what's considered positive and negative. Or you can just do Lenz's law to double check that, separate of the calculation. Okay, so that's one thing. I think you can imagine in a little bit more realistic situation, maybe this isn't perfectly linear, but generally you're going to go from 0 flux when you're out of the field to some maximum flux when you're fully in the field, and you're going to ramp up from 0 to the maximum. And while you're ramping up, you'll get some current in the clockwise direction. Maybe it won't be a steady current in the clockwise direction, but it'll be some current that way. And then nothing while you're in, and reverse as you exit. So other questions that you think could be asked, like what could part C be or part D be? What would other little features of interest be here?
You could probably give us the graph of like everything but the number of turns and see if we can figure that out.
You could say something like, yeah, like if you were told like this is how much current you get, I'm trying to point to this number here, I don't think it was on screen. You know, if you're told this, you'd say like how many pickup turns would you need? Or let's say your goal is to induce at least 0.3 amps of current. You can say, look, how many wrappings am I going to need? Something like that. Like I can't pull it any faster. V is given. Here's the strength of my magnet, so B is given. But one nice thing about induction is if you want to get stronger effects, kind of like get out more wire, kind of, at least from the point of view of voltage. Of course, if you make it a longer wire, its resistance probably increases along with its pickup, its number of turns increasing. So you'll get more voltage if you increase the number of wrappings. Anyways, through that. Here's a couple other things. By the way, this is a fairly common formula. This formula is kind of written just almost directly. What's the induced voltage when you're moving like an object through a magnetic field? And you'll see this BWV, or maybe call it BLV, but in this case, it was what I called the width dimension of loop. That's often called motional EMF. It's an EMF it's an EMF or a voltage due to the motion of an object. And that's a lot of what chapter 33 is about. There are ways to get EMF even when there's no motion. So if you want to do this without any motion, you would probably have a dial where you can like dial up and down the magnetic field. So if I could just if I had a dial that affected the 2.5, I wouldn't have to move anything. I could just set the coil there and I could just dial the B up and down. And that would be my way to get a changing EMF, or sorry, a changing flux. But a lot of times something's rotating, something's moving, something's approaching or receding. Couple more questions here. I'm trying to think how to say without ignoring too much. Let's say you're the person whose job is to keep the loop moving. You're the person that's moving the loop. What would that person kind of experience? They have their eyes closed. They don't know anything about this magnetic field. They got like a string attached to the loop. I don't know. And they're moving along. What would they feel anything? Basically, I want to get at the issue of force. I kind of want to go back a little bit to chapter 32 and say, will there be forces showing up at some point in this process?
I feel like there will be some resistance to movement.
Maybe resistance to movement. Somebody says, is that based on something on the board, or is that based on personal experience? I don't know.
Kind of like the lab we did, like in reverse.
Yeah, maybe when you like wave the magnet around past the sheet, you could feel it or something like that. We could think about that a little bit. So will there ever be a magnetic force on the loop? And if so, when? And if so, how strong? Because we know from chapter 32, I was going to say this was on the test, and it was on the test, but it was one of the two problems where you could do one or the other. But like there was, you know, like a length of wire carrying a current inside a magnetic field experiences a magnetic force. And that was like one of the two questions. You could do a four-sided like little rectangle and say, what's the force in each of the four segments? Or you could do a question about a proton spiraling. Anyways, so let's kind of go to this scenario first of all, because if we can do this scenario, we can kind of figure out the other ones pretty quickly. Let's say we go to this scenario right now. We're fully in the field. We have a really strong flux, but it's steady. So we're not getting any current, you know, no voltage current. So right now there's definitely no current. But what about this one right here? In this case, there is current flowing around this, right? What force will the front edge feel? Because that's a current carrying wire. What force will this little segment feel? That's a current carrying wire. This one won't feel any force. This one won't feel any force. This one won't feel any force. And this one will feel some force. So let's draw like kind of like a free body diagram while you're entering. And by the way, no matter where you're at in the entering process, you know, this is the current amount, the 0.3125. So now I'm going to draw that in. Negative meant clockwise. So while you're entering, you've got current going this way. You've got this amount, which is 0.3125. And I think in symbols or in variables, that would be NBWV divided by R of current. So how much force will the front edge feel, and what direction will the front edge feel of force? What directions of force? To the left. So this edge feels a force like this way. That's like one of the forces. And then this segment feels a force. And this segment feels a force. And what direction they do? Basically, they're going to feel opposite forces and cancel out, but let's just kind of assign the directions. The top edge feels current, has current flowing to the right. It's in a magnetic field that points outward, so I think that's a downward force. So this part feels a downward force, and this part feels an upward force. Is there a net force on the loop due to the magnetic field? There is, and the net force points that way as it moves that way. That's maybe the not too surprising end result if you kind of know Lenz's law that effects oppose causes. Maybe if the cause is a magnet, or sorry, a coil moving to the right, maybe there's going to be some force pushing left. And there is. How strong would that force be? That force would be now. Oh yeah, it would be the current times the length of this wire, which is W, times the magnetic field, which is B, but the current is over here. The current is NBWV over R times another factor of WB. So we get N B squared W squared V over R. I'm not going to do the signs, but you know, you get this force leftward. That's the force while you're entering. What's the force while you're exiting? What's the force when we're part way out of the field? Part way out of the field. Well, now the current is not clockwise. Now the current is counterclockwise. So now the current is flowing this way. And what direction is that force going to be? The really key edge is the trailing edge, and this trailing edge is carrying current down, just like this leading edge previously was carrying current down. So it's switched orientation to current, but now I'm less focused on the front edge and more focused on the back edge, and you basically kind of get like two swaps of direction, and this guy is still feeling a force this way. Yeah, double check, it should be. So what is the force while you're entering? You're feeling an opposing force to the rightward motion. What is the force while you're exiting? You're feeling an opposing force to the motion. And while you're in there or out of there, there's no force. There's no magnetic force. So what would the person experience if it was your job to keep the object going at a steady 0.1 meters per second? Maybe you got to apply a little force, but essentially in physics, you don't have to apply any force to keep something moving at a steady speed most of the time. So you're feeling next to nothing. It's just, I got it going and it's just gliding along. My hand's on it, but I'm not really having to do anything. But then I have to pull for 20 centimeters or 2 seconds to get it in there. And then it glides and I have to pull for 2 seconds to get it out of there. Or you could say you were pulling a little bit, you got to pull more, something like that. Maybe you were opposing air resistance with a modest force. Now you're opposing air resistance plus the magnetic force with a bigger force. How big would this be for our numbers? So the current is 0.3125. I should multiply by this dimension one more time and by magnetic field one more time. So 0.3125 is the current. And then I'm going to multiply that by this dimension, which is 1/10 of a meter. And I'm going to multiply by 2.5 Tesla. So the force for our numbers, I think, should come out to be 0.078 newtons. That's down there. Less shows up on here, and I got to make that bigger. It would help me out in my video. Okay. Helps me see better what they're actually seeing from home or from wherever they're at. So that's one question. That's like one step beyond. So now we've done chapter 32. We've done a really small amount of circuits just to convert a voltage to a current. That's almost nothing. Now we've done chapter 30. Sorry, this is 33. Then a little bit of circuits. Now this is 32. And now I have a question. What do you call a force applied over a distance? Somebody's going to apply this 0.078 Newton force for 20 centimeters, for 0.2 meters, right? What do you call that?
Sounds like work.
So it costs not just force, but it's a force applied over a distance. It costs the person energy or work. They're dumping energy into the coil, into the thing for 2 seconds and 20 centimeters while entering, and for another one while exiting. They're dumping energy in. Where is the energy going? It's not speeding the object up. But what induction is really great at doing, very nice and helpful for doing, is it's really good way to hand energy off from like mechanical energy, like kinetic energy, to electrical energy, or the other way around. If you want to do it one way, we might call it a generator. And if you want to do it the other way, you'd probably call it a motor, especially if you make the object spin instead of like move across. You say, I want to get I have something spinning. Could I turn that into electrical energy? And you're like, yes. Get a magnet nearby the spinning thing and put wires around the spinning thing. And what if you want to go the other way? I have a battery here. I got energy kind of stored up in some electrical form, or at least I have an object, a battery that can access energy and provide it as an electrical form of energy. I'd like to get my toy car's back axle spinning so the car goes like across the room. Induction will be really good at giving you a possible way to do that. You could probably do it lots of different ways. You could design various types of motors, various types of ways to hand the energy off. In particular, one of the things about this is at some point you have to make connection between the stationary stuff and the rotating stuff, because you probably need to make electrical connection to have like there be a completed circuit, but the thing can spin. So the way you make those connections could be kind of interesting and cool, and give slightly different types of output voltages from your motor, or from your generator, excuse me, or slightly different kind of drive characteristics to the motor. And you'll see a wide variety of those. What was I going to say? So where does the energy go? It does not go into kinetic energy. It doesn't go into potential energy, like gravitational potential energy. It gets handed to kinetic, but then very quickly handed from kinetic to electrical current going around the circuit. Ultimately, where does that energy end up? Like when you get to here, ultimately, where did the energy end up? Like what form did it end up in? the resistance or the resistor, whatever the resistance or resistor is, turned it from electrical to something non-electrical again. If there's a light bulb, you lit the light bulb. And probably where does it end up in general? If you tell me there's a resistor, or there's some resistance in some wires, probably like heats things up a little bit, something like that. And you can think of the video of the person melting the, taking 3 minutes and the thing was hovering in the midair and those coils, and it gets glowing and it heats up and it melts it. Because you get some big currents induced in the piece of metal, and it's a pretty good conductor, but if you get enough current, you just sit it there for a long enough time, you're dumping energy in to the current, and the current is crashing, the electrons are crashing into the object, into the atoms that are traveling through, and that gets handed off to heat, maybe, eventually. So that's a good one.
Is that how, like, a decent amount of ovens work?
Not very many, but it could be.
Just heating up coils?
So that would basically be like a resistor, right? We'd probably call it a resistor, a toaster oven. It's got like a filament. You could even use the word filament if you wanted to. Yeah, which wouldn't necessarily rely on any induction stuff. There are induction stovetops. And the idea of an induction stovetop is like, do I really want to heat up, if you just have a normal stovetop, you heat up the heating element, but your goal wasn't to heat up the heating element. It was just to heat up the water or the soup or whatever it is you're cooking. But in order to do that, you probably heat up everything around it quite a bit, and the air gets warmer and the pot gets warmer and all this water gets warmer. What I was just trying, you know what I mean? Like you're heating up a bunch of other stuff that wasn't really the goal. The goal was to get the heat as best we can to the food, to the water, to the, you're going to boil spaghetti noodles or something. So in an induction cooker, the pot becomes the heating element, instead of like the heating element is in the stove and then the heat gets transferred via convection or conduction from the stove top to the pot, from the pot to the water. It's like, hey, what if we just put the current in the pot and then the pot gets warm kind of directly? We can maybe be a little more efficient and kind of get it done quicker, and maybe, with less energy, get the water boiling in less time or with less energy input. What was I going to say? Force. What's the force times the velocity? Force times velocity is power. Sound a little familiar? So if you were to take this force formula, we already squared the B at some point. We already squared the W at some point. If you square the V, if you multiply this by V, then the V gets squared. Then that would be the power that the person pulling would have to provide while pulling the object. And that power should equal what other calculation we can do. That should probably equal I squared R. It should probably equal the electrical power consumed by the resistor, by the resistance. So if you put this over R and then you square it, should I have an N squared? I should probably have N squared here. Anyone think I should have N squared here? This is the force on one of the front wires, and there's 50 front wires. So this is like the force on one wire, and I got to multiply by N. So the N would also get squared. And then if you multiply by V, then that would be power. And that would be everything squared except the R. And the current is NBWV over R. And the power electrically, you could say it's IV. You could say it's I squared R. And I squared R would be N squared, B squared, W squared, V squared over R squared times R over R. So basically that's just a nice little confirmation that we found all the energy. It's really true that all the work or all the power inputted by the person keeping the object going at 10 centimeters per second really is fully accounted for by the electrical power usage by the resistor.
Are you KR cancel amount?
It's I squared 1 factor of R. If you do this with a piece of wood, how much, what's going to happen? It's going to have such a high resistance that nothing's going to happen. Okay, so power, we can find it, make it work. Just take this and multiply by L over V, and I think it would become the work while entering, because you're going to apply this power for what interval of time? Entering time is length of the loop divided by velocity, which loop's moving. Okay, one last question with this. What if we didn't pull it? What if this is outer space and we got the thing moving at 10 centimeters per second, like this first picture, and we just kind of like throw it? We just like throw it at this. What's it gonna do?
If you don't throw it fast enough, it's just gonna.
What if nobody is applying a force on this while it enters? It'll feel this opposing force and it will slow down. Maybe you threw it fast enough and you can get it in the field. Maybe you didn't and it slows down. But there's an opposing force while it's entering, and if nobody's providing a propulsive force for it, it'll just show up as a slowing down of this object. And we saw that, I think, definitely when we dropped some objects, some magnets through some pieces of metal or along a piece of metal. It generally will break it. What would this guy end up doing if you didn't throw it fast enough? It'll just kind of slow to a stop. Because what happens when he slows down a little bit? All this stuff gets weaker. All this interesting stuff gets weaker because it's proportional to the speed, or maybe it's proportional to the speed squared, but it's getting weaker if the speed gets weaker. So he's going slower, but the force gets weaker, and he probably kind of exponentially kind of like drifts to a stop. At which point you've handed off all of the kinetic energy to energy expended through the resistor. Okay. What do we do a little more often? This is the last thing we'll finish it. What do we do a little more often? Like, what if you wanted to generate some current, some voltage and current, but you didn't want to just have it for 2 seconds? What if you wanted to get this to give you something kind of over time? What do we do a little more often than move the coil through the magnetic field? We sit and we rotate the object inside the magnetic field, and you could work out very similar things. Your flux would probably be, in that case, the issue that wasn't a big deal today at all was the cosine theta. That wasn't a big deal today at all. It was cosine of 0 is 1 the whole time. But if you rotated it, the area of the loop is like, well, the entire loop could be inside the field the whole time. So A is the full area. B maybe doesn't change. And then everything would come from the cosine going through high, low, high, low, high, low, as you go from maximum positive flux to 0 flux, maximum negative flux to 0. And basically, what if you rotated the loop at a consistent angular velocity? Then theta would be omega t, and then you have a function of time for flux, and you could take the time derivative. So I think I'm just gonna write that here really quickly. What if you rotate a coil at angular frequency, or you could say angular velocity omega, fully, well, just to be clear, fully inside a magnetic field. And we'll assume the magnetic field is generally uniform. It's about the same strength. If you do this, then what's your flux function? Magnetic field times area of loop times cosine omega t. And if you wanted to, omega is 2 pi times frequency, which is 2 pi over period. Does this sound okay here? What's the difference between omega f and t? And I don't just mean now, I mean like basically all the time in any context, capital T, I guess. Radians per second. This is hertz or cycles per second, but how many radians are in a cycle? 2 pi radians per revolution. And this is second. I guess, yeah, I'm not going to do the minus sign. D phi dt. So what is the time derivative of this? We have the n, we get the b factor, we get the a factor, and then the derivative of cosine omega t would be omega. Maybe I'll put, yeah.
Put the negative
I'll put the minus sign back in because I'll get another minus sign, won't I? Times negative sine omega t. That's the time derivative. So NBA omega. And if you want, you could write 2 pi f times sine omega t. So what do we have here? We have a flux, which is, sorry, not a flux, a voltage or an EMF, which is being continuously generated. And what would this output voltage look like? It's sinusoidal with this amplitude. You know, we're just going to kind of be, we're going to be getting this kind of output where these peak values are N number of wrappings, B magnetic field strength, A area of the coil, times something about how proportional to how fast you're rotating it. If you want to write 2 pi f, write 2 pi f. If you want to write 2 pi over t, you could write 2 pi over t. And that would be basically a generator. If you run this system backwards, or kind of you get the same effects handing it off the other way, you'd probably call it a motor. So I've got the battery, I want to turn the axle, I'll use induction and I'll rotate the axle, I'll call it a motor. What do we got? We got rotation. I don't know where the rotation came from, but somebody's rotating this. Maybe somebody's on a little stationary bike and they're pedaling. Maybe there's a waterfall and the water is going over a cascade and it's turning a turbine. Maybe somebody's heating, maybe they're burning coal or something and the steam is rising up and it's turning a turbine, but something got something turning. And if we have something turning kinetic, mechanical type energy, here's a way to hand it off to electrical energy, because basically at the two ends of this coil, you got a voltage that's oscillating. What kind of voltage do we have? What kind of circuit do we have? We have a alternating current is pretty naturally produced from induction topics, pretty naturally produced. And I drew this as a sine, but I don't really care if it's a sine or a cosine, just that it's sinusoidal, and the period would be the same as the rotational period. And then the amplitude is proportional to these features here. More wrappings, stronger field, bigger area, turn them faster. Turn them in less time. I think that covers most of it. I think there might be one question in the homework this week that, what would typical questions be? Find a voltage or find a current? Find an induced effect, which is going to be electrical in nature, voltage or current. I think there's one question that says, find the strength of the induced electric field, instead of saying find the strength of the induced electric current or voltage. So that one, you might want to look and see some other examples of, I think they work out a problem quite a bit like it in the book. That one's a little tougher. We'll probably talk about that one some on Friday. Tomorrow's lab is quite different than this. There's going to be lights and little bulbs and mirrors and lenses and things. Here's a good question you can think about for tomorrow's class. Ready? what is the smallest mirror it would take to see your whole self head to toe in the mirror? How big of a mirror would it take, and where would you stand, and where would the mirror be? Yeah, you can think about that. We'll talk about things kind of like that. Reflection and refraction is a topic for tomorrow's lab. Pretty different, but we'll get there. And the test should be graded by then and back. Pretty confident of that. Morning. Can I talk to you about this? I gotta remind myself what it is. This is really good. So there's the two problems. There's this one. So all the R's are the same. So I see you writing like RV for vertical and like RH. Maybe on the other one, RHs. They're all R's.
Okay.
So, it simplifies some stuff, maybe based off of that. Like, these are, I think that's probably like correct, but like H and V, H1, H2, V1, V2, those are all just some resistance constant R.
Okay.
And I'll tell you, the answer for D is not infinity.
Yeah.
Although this is true, I think this is true. The new equivalent resistor, I think that's true. It ends up not approaching infinity. So here we go. And then this one, I think you kind of like labeled all these when we were doing this. This kind of, you said I1s and you put some I2s and you put some I3s, and those are all right, I'm pretty sure. So then how do you figure out the value of I1? So like how do you figure out the value of I1 and I2? It's not, I think this is true. Like current in is I1, I1, I2. I think that's good. And then maybe you said I2 is I5 plus I4. Does it say that somewhere? Yeah, so I think those are good. But how do you go to actually figure out that I2 is a third or I1 is like some other particular fraction? So if do you feel like the same line of current goes this way, this way, and this way? The whole point of like identifying one of them as I2 and the other one as I1 is to say, I feel like based on the shapes, these guys got over it, but I feel like there's no requirements going into it that these all that two guys would stay with that. And they're not the same, obviously. So you got a node rule at like A and B, same spot. You have 4 node rules, and you do a bunch of stuff. How many equations did you get here overall? Yeah. And how many currents do you have?
5.
You have 5. So, so you need one more equation.
Yeah.
I mean, you're like 80 or more % of the way there in some sense. Where else could you go to get the equation? You've done those. You could maybe do a loop. Now, some of the loops aren't going to tell you anything. What if you do loop rule for the right front fix? I1 against I1 against I1. It's already going to be fine. And I think the back face is kind of something similar because you figured out by nodes of I4 and I2. So if you do, like, I think any of the side kind of panels, you'll get one more equation.
Okay.
And then you can actually get some fractions and you'll find that it's not a third.
Okay.
Do you want to try that?
Sure.
You can try it. And I think it's something similar here. Something similar here. I don't know how many node equations you have, but you're going to need to throw in a loop equation there too. And then you'll get fractions like eighths or fourths or sixths or something.
Okay.
Good try. What do you got there?
It's the last question on the homework.
Okay, yeah.
Do you remember it? It's
the
yeah.
wire and
Yeah.
it's moving away from the wire.
Okay,
So it's
and does it say how
changing-
fast it's moving? Does it
does.
say it moves from A to B or something?
It's
Okay.
just one spot and that's how fast it's moving.
Okay, so just like at this moment, what will the voltage be or what will the current be?
It was
They're almost
I can't
the
remember. It
same
was current
question.
voltage, one or two, but
Yeah,
it
they're
had either
basically-
resistance, so it doesn't really matter.